All right, in section 1.8, we're going to talk about acceleration models. Now, we did problems earlier where we talked about acceleration, but in those problems, acceleration was always a constant. And when acceleration was a constant, velocity turned out to be a linear function, and position always turned out to be a parabola, a quadratic function. In this section, we're going to deal with problems where acceleration is not necessarily constant. So you end up with more complicated things. Can you give me an example of something where acceleration might not be constant? When there's air resistance. So when we did problems before where we threw a ball up in the air, we always assumed there was no air resistance. Now we're going to assume there's air resistance.
We're not in that physics perfect world anymore.
We're not in that physics perfect world anymore. We're getting more towards reality. We're gonna deal with wind resistance, wind drag. What else? A roller coaster. What happens with a roller coaster?
Certain points it's decelerating or accelerating.
The roller coaster goes up and down, so sometimes it's decelerating, sometimes it's accelerating. But is the acceleration constant though?
Maybe probably based on the slope that it's going over.
Okay, you would have friction resistance there, because the acceleration due to gravity is still constant there. But I would agree you would have friction resistance. I don't think there's any roller coaster problems in the book, but that could be a good example, yes. Okay, you could be dealing with a spaceship landing. And so you've got the acceleration due to gravity pulling you down, and then you're firing the thrusters, and your thrust might change. You might be going too fast, and you realize you need to put the brakes on more so you don't crash. There is a game called Lunar Landing where you can practice that sort of thing. That's right, that's an old game.
That was mad touchy.
Yeah.
Literally had to like.
Pretty sure it's touching going too.
I'm pretty sure it's touching real life too.
Yeah, but they put springs and safety factors in there. Let's get it like.
All right, so let's take a look at number 3. Number 3 says, suppose that a motorboat is moving at 40 feet per second when the motor suddenly quits, and that 10 seconds later the boat has slowed to 20 feet per second. Assume, as in problem 2, that the resistance it encounters while coasting is proportional to its velocity. How far will the boat coast in all? All right, so let's start with the important words here. Suppose that a motorboat is moving at 40 feet per second. What's that? That's the initial velocity. So this is page 93, number 3. Its initial velocity was 40 feet per second. When its motor suddenly quits, and that 10 seconds later, the boat has slowed to 20 feet per second. So what's that? I don't think that's V final.
V at 10 seconds.
That's V at 10 seconds. V at 10 seconds is 20 feet per second. Assume that the resistance it encounters while coasting is proportional to its velocity. All right, so what does that mean? Resistance is proportional to its velocity. We're going to call it its velocity, its acceleration is proportional to its current velocity. So when it's going fast, it slows down fast. As it's going slower, it slows down more slowly. So this is your acceleration. Your acceleration is proportional to your velocity. And then it says, how far will the boat coast in all? So what do we want to know?
V final 0.
We want V final to be 0, and then we want to know position at that time, because we want to know how far did it coast. So eventually that boat comes to a stop. When that boat comes to a stop, how far has it gone?
So initially it was at 0, let's say.
Right, so we're going to assume we're going to call our initial position 0. And we'll see how far it went from there. All right, well, we've got a differential equation here. dv dt equals minus kv. What kind of differential equation is that? Separable. dv over v equals minus k dt. We integrate. ln v equals minus kt plus c. We exponentiate, and we get velocity is c e to the negative kt. And then we have 2 points of reference, which should allow us to find both c and k. All right, so let's start with this one, I guess. That one says 40 equals c, because when I plug 0 in for time, e to the 0 is 1. So we know v is 40 e to the negative kt. Plug in my other point, 20 equals 40 e to the minus 10k. Divide, a half is e to the minus 10k. Apply logarithm on both sides. So k is ln of a half divided by negative 10. It's very similar to a half-life, except this is a half speed, isn't it? We went from 40 to 20. That's a half speed problem. Very similar to half-life.
Is it all kind of like similar? Just like you use a similar equation to do different things?
Yes, this
I like population acceleration.
this form c e to the negative kt. This comes up all the time. This comes up. This is your exponential growth model. It's your exponential decay model. Here it's coming up as a velocity model. I agree. That form comes up all the time. Very, very similar in a lot of different problems. All right, so we have at this point v equals, what did we end up with? 40 e to the ln 1/2 over 10 t. Because I did have a negative there, but I've got another negative there, negative and a negative, make that a positive. Great. What's next?
Final is 0, so you can find t.
What's that?
You can find t final by plugging in 0 for v.
All right, if I plug in 0 for v, I get 0 equals 40 e to the ln 1/2 over 10t. And I'm going to have a problem. What's my problem? If I divide by 40 and then I try to do the ln, I can't do the natural log of 0. So I got a problem.
So
Can you bring up the
derive it to find one.
I could break this up. It doesn't really help though. I can't get rid of that e as a problem because I got to do an ln. I can't get rid of it.
Is it negative then?
It was negative, but remember we had another negative here in our formula. So negative and then this negative down here. 2 negatives made it positive there. Nope, I don't integrate it. Oh, well, I do integrate it to get something. I am going to integrate it. What's integrating it going to give me?
Position.
It's going to give me position. But I'm going to need a time eventually, aren't I? I need a time number to plug in. But I can't solve for t. I feel like I'm in an infinite loop here. When does the boat come to a stop?
When velocity is zero and acceleration.
Never.
The boat comes to a stop when velocity is 0. When's velocity 0?
Never.
Theoretically.
Theoretically, never. But what's going to happen?
It's going to approach.
This boat is going to come to a stop as t approaches, not 0, infinity. Because ln of a half is a negative number. If you don't believe me, type that into your calculator. ln of a half is a negative number. So this is a negative power. So as t gets really, really big, I'm going to end up with e to a really, really big negative number. E to a really, really big negative number gets really, really close to 0. So v approaches 0 as t approaches infinity. So what we're going to want to do is we're going to want to find the position function, and then we're going to want to take the limit as t goes to infinity. So according to this, in theory, the boat never stops. Right? Because we cannot solve that equation. So in theory, the boat never stops.
So we're done. That's a photo credit for the test.
No. All right. So good try. We need to find our position function. We know our velocity function, but we remember that velocity is, of course, the derivative of position. So we have ds dt, where s is position. ds dt is 40 e to the ln 1/2 over 10 t. How do you solve that equation? Well, before I integrate, I think I better, it's separable, right? ds is 40 e to the ln 1/2 over 10 t dt. So I integrate. I have s equals. What's the integral of 40 times e to the ln 1/2 over 10 t? It is a U substitution problem. Well, let me ask you a different question. This is something you might remember from Calc 2. What is the integral of e to the kt, where k is just a number? This is 1 over k e to the kt. The derivative would be k e to the kt. The integral is 1 over k e to the kt. That's exactly what we have here. This is just a number. So we're going to have this 40 is going to survive here. Then we're going to have 1 over ln of 1/2 over 10. We're going to have this e, ln 1/2 over 10t, plus, need a letter, z, because I already used c up here, I already used k up here, I need another letter. Z sounds like a good letter.
Do you have written that as 10 over ln 1/2?
In fact, I'm going to flip and multiply. So this is 400 over ln 1/2 e to the ln 1/2 over 10t plus z. All right, almost done. What's left to do? No, I don't want to do natural log. S of 0 is 0. All right, so that was our initial condition way back up here. S at 0 is 0, which should allow us to find a value for that z number.
Because t will be 0.
So let's see. S at 0 equals 0. That gives 0 equals 400 over ln 1/2. But this is going to be e to the 0, which is 1 plus z. So z is minus 400 over ln of 1/2. All right, so our position equation finally becomes S equals 400 over ln of 1/2 e to the ln 1/2 over 10t minus 400 over ln of 1/2.
Are you sure we have to do 2 of these problems on the test?
No, you only have to do one of these, and then you get to pick one of something else. So now the question is,
Thank you for giving us extra.
you're welcome. How far did the boat go?
Too far.
Well, as t goes to infinity, what happens to this e thing?
It becomes 0.
It becomes 0 because, again, this ln of 1/2 is a negative number. So when t goes to infinity, this e thing becomes 0. 0 times this thing is 0. So when t goes to infinity, how far did the boat go?
But it's not truly negative because ln of 1/2 is a negative.
Right, so we really have a negative divided by a negative. We do truly have a positive answer there. So our answer is, how far did the boat go? Negative 400 over ln of 1/2. That's how far the boat will drift. Questions on that?
No, we got rid of 1.
No, there was no y at all in this problem. There were v's, there were t's, there were k's. We used just about every letter except y.